Thank you guys for joining me in this video. In this one, we are going to figure out how to calculate the average shear stress. The average shear stress in a very simple way, tau average equal V divided by area. V is the applied shear force, area is the cross section of the member. So for example, if the applied shear force is F and the cross-section area of this member is this one, go ahead and divide the applied force or the applied shear force by the area of the cross-section. You can get the average shear stress. This one is average, not accurate shear stress, but it's average shear stress, tau average. And keep in your mind and remember, sometimes we have single shear and sometimes we have double shear. If you look here, this bolt is connecting between two plates and one more. So we should expect shearing at this surface and another shearing at this surface. So it will be called double shear, double shear, double shear. But this one is connecting between two plates only, so we expect shearing at this surface between the two plates, so it will be single shear. What is the main difference between both of them? It's very important to understand that this section will support only half of the applied force, and this one will support only half of the applied force. But in this one, this surface or this shearing surface will support the whole force, F. So if you would like to be more accurate, I do recommend to say that the tau average, the average shear stress equal the applied shear force divided by N time area. The applied shear force divided by N time area. This to be more accurate. Area is the cross section of the member. V is the applied shear force. N is the number of shear planes. Or N equal 1 if we have single shear, N equal 2 if we have double shear. Sometimes we have triple shear. In this case, the N equal 3. So be careful that not all the applied force will be used to figure out the average shear stress, but we have to consider if we have single shear, double shear, triple shear, whatever. So to be more specific, to be more accurate, I can say the average shear stress equal V divided by N time A. V is the applied shear force. A is the cross section, and N based on the number of shear. Is it single shear, double shear, triple shear, or whatever? Single shear, N equal 1. Double shear, N equal 2. I have the first example related to the average shear stress. We are given a beam, AB, supported by a hinge at A, and this hinge is supported by a bolt with connected to the beam in this detail, and this detail showing you that we might have two planes of shear, this one and this one. So this one will, or this connection will be double shear. Double shear. This is the first note. If you look to the connection at B with this cable BC, this connection looks like we have only shearing at this contact between the two bars, so it will be single shear. This is the first note. This is the first note. But I have to start with engineering mechanics because I have to figure out the force in this member or this cable BC and what are the reactions at A. These reactions or this force will be used to figure out the average shear stress. We are looking to figure out what is the average shear stress in these 20 millimeter diameter pin at A and 30 millimeter pin at B. So I'm gonna start with the engineering mechanics part to figure out the reactions. I'm gonna draw the free body diagram for this beam. It is a beam AB. I have two reactions at A, YA, and XA. I'm gonna assume it in this direction. I am given applied force at this point 30 kilonewton. In member BC, it's a cable member or two force member or link member. That means I'm gonna have only one reaction in member BC. This reaction with inclination and the right angle triangle 3/4 is given. So I can break this reaction to two components. If you assume this is your angle theta, so I will have R cosine theta, and this is the vertical component R sine theta. Just to keep in your mind, this angle theta will be equal to this one. So sine theta will equal 4/5. Cosine theta will equal 3/5. That means I can say this term is 3/5. And this term is 4/5. So I am ready. I am ready. I can apply the equilibrium equation. Summation f of x equals 0. I have negative xa. I have positive 3/5 r equals 0. Summation f of y equals 0. I have positive ya. I have negative 30. I have positive 4/5 r equals 0. The third equilibrium equation, I'm going to take moment at any point. I'm going to take moment at point A. And that equals 0. I'm going to assume the clockwise direction is my positive. This part is the engineering mechanics part to figure out the reactions for this beam. If you take moment at A, so XA time distance, YA time distance, 30 time distance, 4/5 R time distance, 3/5 R time distance equals 0. I have to list everything to be included in this equation. So I'm sitting at A. So the distance between XA and A 0, YA and A 0, between 30 and A 2 meter, between R 4/5 R, which is the vertical component, and A, the horizontal distance is 6. Between 3/5, the horizontal component, that means I'm looking for vertical distance. We don't have vertical distance between this point B and point A. This term will be cancelled, cancelled, cancelled. I think 30 times 2 will be positive, clockwise. 4/5 R times 6 will be negative, counterclockwise. So I can figure out the value of R. If you figured out the value of R, it will be 60 divided by 4/5 times 6. It will be 12.5. So this R equal 12.5 kilonewton. If you put R here 12.5, I can find out the value of XA. If you put R here 12.5, I can figure out the value of YA. So XA will be 12.5 times 3/5. It will be 7.5. 12.5 times 4/5 minus 30. So YA will be 20. So this reaction equal 20. This reaction is 7.5. And this R equal 12.5. This is for engineering mechanics to figure out the reactions at A and B. I'm gonna start with A. For support A. At point A, we have a horizontal reaction like this, 7.5. We have a vertical reaction like this, 20 kilonewton. So the total or the resultant force at A equals square root 7.5 square plus 20 square. All of them under square root. This is the resultant force at A. So 7.5 square plus 20 square under square root. The value will be 21.36 kilonewton. I would like to highlight this point one more time. Guys, if we have two forces, one in this direction, 7.5, and one in this direction, 20 kilonewton, we need to figure out what is the resultant force for the two forces, the horizontal and the vertical one. From engineering mechanics, we learned that R equal square root for the horizontal component 7.5 square plus the vertical component square. We got the resultant force of the two forces. Keep in your mind the average shear stress, equal the applied force V divided by N time area. We are talking about support A. So the applied force equal 21.36 kilonewton. This is the resultant of the two reaction at A. YA and XA, both of them will give you a resultant force at A that will be supported by this bolt or this pin. Number of shear planes, we have double shear at A. Based on this detail, the shear will be double. That means the N will be 2. The cross-section area of the bolt at A with the diameter 20 millimeter, it will be pi divide 4 times this diameter square. That makes sense? I do recommend to multiply this 21.36 by 1000 to be in, just a moment, to be in Newton. That makes sense? So one more time, the applied force for shear at support A will be the resultant force for the two reactions. N, the number of shear plane. We have double shear, so N will be 2. The area is the area of the cross-section of the bolt at this pin, at this support. The diameter of this bolt equal 20 millimeters, so pi divide 4 times diameter square. So the average shear stress will be 33.99 Newton per millimeter square, which is mega Pascal. This is the average shear stress in the 20 millimeter diameter pin at A. For B, we have this resultant force R, capital R. So for support B, the average shear stress equal V divided by N time area. The applied shear force or the applied force at support B, the resultant, we have horizontal and vertical component. I don't care. We have only one resultant force R, 12.5 kilonewton. I'm gonna multiply it by 1000 to be in Newton. The number of shear planes, since the details given at this support B, it's only the single shear. So the value of N will be 1. The area of the bolt or the pin at B, we have 30 millimeter diameter. We have 30 millimeter diameter. So the area will be pi divide 4 times 30 square. So I can figure out the average shear stress at B. It will be 17.68 Newton per millimeter square or mega Pascal. So we started first with the engineering mechanics part to figure out the reactions. If we have hinge support like this one, we have two reactions, horizontal, vertical. Then we need to figure out the resultant force for these two reactions. Then at B, we have only one member, so the force in this member equal R. We found the force in this member. Then we can apply the average shear stress equal the applied force divided by N time A. Based on the number of shear, is it single shear or double shear, we can figure out the average shear stress. We have one more example. In this example, we have a beam supporting many concentrated force. This one equal 15. This one equal 60. This one equal 60. This one equal 30 kilonewton. So the P value equal 15. So P equal 15. 4P will be 60. 4P will be 60. 2P will be 30. And at B, we have a member, BC. This member is connected at C with this detail, which is double shear. This one is double. Looks like we have two plates, so we should expect shearing and at two planes. And this one also at B, it's a double. And at A, we have this detail, which is double also. So all of these connections are considered double shear. So N equal 2, N will equal 2, and N will equal 2. And all of these connections with a diameter, the pin or the bolt with a diameter 18 millimeter. And also all pins are in double shear. This information is given. Whatever. I have first to start with the engineering mechanics part to figure out the reactions. Keep in your mind, this beam is supported at A with a hinge. That means we will have two reactions, YA and XA. At B, we have a member BC, so I will have a force or a reaction R in member BC. Keep in your mind, we have concentrated force, concentrated force, concentrated force, concentrated force, 15 kilonewton, 60 kilonewton, 60 kilonewton, 30 kilonewton. Before starting to apply the equilibrium equations, I have to break this force R to R cosine 30. This angle is given 30, and we have R sine 30. I am ready to apply summation f of x equals 0. I have negative R cosine 30. I have positive XA equals 0. I can apply summation f of y equals 0. So I have positive R sine 30 minus 15 minus 60 minus 60 minus 30 plus YA equals 0. I'm gonna take moment at any point. I maybe take moment at A. So I'm gonna take moment at A equals 0. I'm gonna assume the counterclockwise rotation is my positive. So I have XA time distance. I have YA time distance. I have 30 time distance. 60 time distance. Another 60 time distance. 15 time distance. And we have R sine 30 time distance. And we have R cosine 30 time distance. I have to consider everything in this equation. Sometimes the term has a zero force, zero distance. So for example, I'm sitting at A, so the distance between XA and A 0, YA and A 0, between 30 and A is 0.5, between 60 and A is 2, second 60 and the A is 3.5, wait. This one is 2, this one 3.5. And the 15 and the A, we have 3, 4.5. Between R sine 30 and the A, the total length is 5. For R cosine, it's a horizontal force. We don't have vertical distance, it will be 0. This term will be cancelled, this one cancelled, this one will be cancelled. This force will be counterclockwise positive, counterclockwise positive, counterclockwise positive, counterclockwise positive. This one is clockwise, will be negative. The only unknown is R. So I can figure out the value of R. It will be 30 times 0.5 plus 60 times 2 plus 60 times 3.5 plus 15 times 4.5 divided by 5 times sine 30. This R will be 165 kilonewton. If you put R here, 165, I can figure out the value of XA. It will be 142.9. If you put R here, 165, I can find out the value of YA. It will be 82.5 kilonewton. So let's start with A. For support A. For support A. Support A, we have two reactions, XA and YA. We have XA like this and YA like this. XA equal 142.9. And YA equal 82.5. So the resultant force R at A will equal square root for 142.9 square plus 82.5 square. So the resultant force will be 165 kilonewton. Okay, that's fine. 165 kilonewton. So the average shear stress at A will equal V divided by N time area. The applied force at support A, which is the resultant, equal 165. I'm gonna multiply it by 1000 to be in Newton. We have double shear, so we have N equal to the area, the bolt or the pin has a diameter 18 millimeter. So by divide 4 times 18 square, this is the area. So the average shear stress will be 324.2 Newton per millimeter square, which is mega Pascal. For connection B. At connection B, we have a resultant force R equal 165 kilonewton. And the average shear stress will equal V divided by N times A. V equal 165. I'm gonna multiply it by 1000 to be in Newton. N double shear 2. The area by divide 4 times 18 square. I'm gonna get the same number, 324.2. For connection C, we have everything is the same. Connection C, connecting this member, and the force in this member is 165. So the average shear stress will also the same for C. This one for B, this one for C, it will be 324.2 megapascal. Does that make sense? So to solve this kind of problem, we have first to start with the engineering mechanics part to figure out the reactions. Once you get your reaction, then I can apply the average shear stress equation equal V divided by N by A in how many shear plane or shearing failure, single or double or whatever, and what is the cross-section area of the bolt and what is the applied force. That makes sense? The last example in this video, we are given two members, this member and this member, connected together with welding. And the welding is done on a plane with angle 30 degrees from the horizontal. And this member under the effect of two forces, looks like these two forces are pulling, so it's tension, 800 pound. We need to figure out what is the average normal and the shear stress on the plane of each weld, which is this one and this one. So keep in your mind, if you decided to use the right part, 800 pound, this inclined plane and this inclined plane, we will have a force here for 100 pound, and we will have a force here for 100 pound to make a cropping. And also the problem said this, assume each inclined plane supports a horizontal force of 800 pound. That makes sense? So we need to calculate how much average, normal, and the shear stress on this one and also on this one. If you did for one plane, it will be the same on the other one. So the idea is we cannot divide 400 pound by the area. Do you know why? Because this inclined surface under the effect of a horizontal force, 400 pound. Unfortunately, I have to break the 400 pound to two forces, one perpendicular to the cross section and one parallel. So 400 pound must be broken to a perpendicular force to the cross section, because this force, which is perpendicular, will cause normal stress. And I have to break 400 pound to a force parallel force to the cross section, because this force, which is parallel to the cross section, will cause shear stress. That makes sense? This point is very important. Keep in your mind, this angle is 30. So this angle will be 30. So this component will be 400 sine 30. And this component will be 400 cosine 30. That makes sense? Also, what will be the area of this inclined surface? Because we need the area to divide the force by the area. Keep in your mind this distance, which is inclined, and this distance, which is given 1.5. This one is 1.5 inch, the thickness of the member. So how can I figure out the inclined distance for this cross section? I have to use the right angle triangle. So if we clean up this one, just look here, we have this triangle. This vertical distance is 1 inch. This angle is given how much? 30 degrees. So this one is 30. So I can figure out the inclined distance by saying sine 30 equal the horizontal, the opposite dimension 1 inch, divided by this length. So I can find out the length of this inclined plane. It will be, I think, 2. Yes, 2 inch. I would like to highlight this example one more time. So guys, we have this inclined plane or plane like this. So we have a force here, 400 pound. First of all, the area of this cross section equal 2 inch by 1.5 inch. I figured out this 2 inch using the right angle triangle. That makes sense? This one. Second, keep in your mind, this force 400 will be broken to two components, one perpendicular to 400 sine 30, and another one here 400 cosine 30. So the average normal stress equal the force divided by area. The applied force perpendicular to this cross section is 400 sine 30, which is positive. Pulling, not pushing. Pulling is the cross section, so this one is tension. So the stress will be positive. Divided by the area, which is 2 inch by 1.5 inch. So the area, the stress will be 400 times sine 30 divided by 2 times 1.5. This stress will be 66.67 positive pound per inch square or PSI. For the average shear stress, equal the force parallel to the cross section, which is 400 cosine 30 divided by area. We don't have here double shear or single shear. It's only one. So the N here will be 1. So the applied force 400 cosine 30 divided by 1 time the area of this cross section 1.5 inch times 2 inch. So the shear stress will be 400 times cosine 30 divided by 3. So the stress will be 115.5 psi. We don't have positive or negative for shear. We have only one value equal 115.5 psi. So the main idea in this example, 2 points. The first point, first, what is the area of the cross section? This area. So I have to figure out this length and this width is given. The second idea is the applied force on this plane is 400 pound. I have to break it to one perpendicular and one parallel. So I break this force 400 pound using the given angle 30 to two components, one perpendicular and one parallel to the cross section. Once you get the forces on the cross section and you have the area, just go ahead and divide the force by area, the force perpendicular to get the average normal stress, the force parallel to get the average shear stress.